You know, all of human history can be told through the materials we've mastered. We had the Stone Age, the Bronze Age, the Iron Age. But what age are we in now? Well, we're stepping into something entirely new. An era where we don't just find new materials, we actually design them from scratch, right inside a computer. And today, we're going to look at one of these brand new computer-born materials that could totally reshape our future.
And this really gets to the heart of it. We're facing a couple of huge roadblocks right now. Our computer chips are pretty much as small as they can get, and we're wasting a mind-boggling amount of energy all over the world. So here's the big question. What if the answer to both of those massive problems was the exact same thing? So to really get why one new material could be such a game changer, we have to understand the walls we've actually hit. And look, this isn't just about making our phones a little bit faster or trimming a few bucks off our power bills. This is about breaking through some fundamental limits that are holding back, well, the entire next wave of innovation. Okay, so on one side, you've got electronics. Moore's law, the engine that's driven tech for 50 years, is kind of sputtering out. We just can't physically shrink the parts any smaller. And on the other side, there's our energy problem. It is shockingly inefficient. Just think about it for a second. The heat pouring off your laptop, your car engine, a factory smokestack, that is all just lost energy, completely wasted. These two problems are, without a doubt, two of the biggest challenges we face today. So, how in the world do you solve both of those at once? Well, not by getting lucky and digging something new out of the ground. You do it with pure design. So let's meet the hero of this story, a whole family of materials that was dreamt up, built, and tested inside a supercomputer before anyone ever touched it in the real world. And here it is. Now, don't worry about the crazy chemical name. What's so amazing is how it was made. Scientists use these incredibly powerful computer models to build it and test it, all virtually. You can think of it like the ultimate digital chemistry set, where they could see how every single atom would behave. And what they saw was that this material didn't just have one superpower, it had two. All right, let's dive into that first superpower, the one that could solve our electronics problem. We're not just talking about a small upgrade to the chips we already have. No, we're talking about a completely new type of electronics, a whole new field called spintronics. So what on earth is spintronics? Well, for 100 years, every electronic device you've ever used has worked by just moving an electron's negative charge around. But electrons have this other cool property called spin. You can kind of think of it as a tiny built-in magnet that can point up or down. Spintronics uses that spin, that magnetic direction, to hold data. And if we can get it to work, it could lead to devices that are insanely fast and use way, way less power. But of course, there's a catch. There's always a catch, right? For decades, the only materials that could do this spintronics magic had to be kept incredibly cold, like liquid nitrogen cold. Totally impractical for your phone or your laptop. So the holy grail, the thing everyone's been searching for, is a material that can do this trick at normal, everyday room temperature, and hopefully even hotter.
And this is where our new material just shatters all expectations. The computers predicted it would have a Curie temperature of 710 Kelvin. Now, to put that in perspective, room temperature is about 293 Kelvin. This means our material keeps its amazing magnetic properties way past room temperature, all the way up to over 430 degrees Celsius, or 800 degrees Fahrenheit. That's not just a step forward, it is a giant leap.
And the simulations even show us why it works so well. I know this slide looks really complex, but just focus on the gap between the pink lines and the blue lines, right where the arrows are pointing. That gap represents a huge difference in energy between electrons spinning one way versus the other. It's like having a really, really clear on and off switch. That big, clean separation is exactly what you need to build spintronic devices that actually work. Okay, so superpower number one, revolutionize computers. That's pretty amazing on its own. But that is only half the story. Remember that huge problem with wasted energy? Well, this material's second superpower tackles that problem head on. It can turn heat directly into electricity. This amazing ability comes from something called the thermoelectric effect. And it's a really cool idea. Basically, if you take a piece of this material, heat up one side, and keep the other side cool, the material itself starts generating electricity. Just imagine being able to slap a device onto your car's exhaust pipe or a factory smokestack and have it create power out of thin air from the heat that's already there. Now, for this to work really well, you need a material that's kind of weird. It has to be great at moving electricity, but awful at moving heat. You need to keep one side hot and one side cold. And as you can see here, our material is a fantastic heat insulator. For comparison, copper, which is great at conducting heat, has a value around 400. This stuff, it's down at 2.2. It holds on to heat beautifully, which is perfect for this job. Okay, so how good is it really? Well, scientists have an efficiency score for these materials. It's called the figure of merit, or ZT. For years, the big goal in the field was to find a material that could hit a score of 1.0 at room temperature. That was considered the threshold for it to be actually useful. And K₂GeMnX₆, it clocks in at 1.01. It hits that mark, making it one of the best thermoelectric candidates ever discovered.
And the computer models back this up with even more proof. This graph shows what's called the Seebeck coefficient. It's basically just a measure of how much voltage you get for a certain amount of heat. But you don't need to be a physicist to get this one. Just look at that huge spike on the top left graph. That peak tells you everything you need to know. This material has a really, really powerful response to heat. It's a big deal.
So at this point, you're probably thinking what I was thinking. This sounds way too good to be true. A material with two incredible, world-changing superpowers, all just predicted by a computer? So the next question is the most important one of all. Is this stuff actually stable? Could you even make it in the real world?
And the simulations came back with a big yes. This graph here shows the material's energy. See how the line dips down into that deep valley? That's the sweet spot. It's like a ball that's rolled to the very bottom of a bowl and has settled in. That tells us the material has a very stable, low-energy structure. It wants to exist in this form. But what about vibrations? The atoms inside any solid are constantly shaking around. And if those vibrations aren't stable, a material can literally just shake itself to pieces. These graphs model those vibrations. And the only thing you need to notice is that all the lines are above zero. That's the sign we're looking for. It confirms the material is dynamically stable. It can handle its own internal jitters.
And finally, the last test. Could you actually work with this stuff? Is it tough and flexible like a metal, or is it going to shatter like glass? The researchers ran all the numbers, Pugh's ratio, Poisson's ratio, Cauchy's pressure. I know it's a lot of jargon, but they all point to the exact same conclusion, which you can see in that last column. The material is predicted to be ductile. That means it's tough, not brittle, and that's absolutely crucial if you want to manufacture anything with it. So when you put all of this together, what does it really mean? Well, it's about way more than just this one cool material. It's about a whole new way of inventing things. We are looking at the beginning of a true materials revolution, one that's going to be powered by computers. Because this material has this amazing combination of properties, electronic, magnetic, thermoelectric, even optical, it's not a one-trick pony, not at all. It could be the key to so many things. Those next-gen spintronic computers, systems that pull electricity from waste heat, much better solar cells, new kinds of LEDs, and all sorts of advanced sensors. It's a genuine multi-purpose powerhouse. And hey, don't just take my word for it. This is a direct quote from the scientists who did the research. And you can feel their confidence. They're not just saying this is a neat idea. They're saying this material has real potential across a huge range of important technologies. The possibilities are just enormous. And that really leaves us with one final big thought to chew on. This entire discovery, from the first idea to the final proof, it all happened inside a computer. We now have the tools to design a material with a specific superpower to solve a specific problem. So the question isn't just, what new things can we find out there anymore? The question is, what should we build? Now that we have these incredible tools, what global problems should we point them at next?